The IDP project introduction is presented by me, Sherason Elista Dingwan, WETIC number 73827. A semi-automated boat represents a type of watercraft that incorporates a combination of manual control and automated system for navigation, propulsion, and various functions, which enhances their capabilities and improve overall efficiency. There is a need for transportation of nipa sep at Sungai Sabang, Kota Samarahan due to their lack of sustainable water transport system, which can be inefficient, costly, and less environmentally friendly. Therefore, 5 objectives have been established by Center Inc. in regards to the problems as shown in this slide.
Hi everyone, I will present the board overview. On the left side is the board design in AutoCAD and the right side is the model of the board. In the first video is to demonstrate how the semi-automated board works in a real situation using the board model. Other than that, our board has a radar system that is controlled using remote control. Next, a ultrasonic sensor which is attached in front of the board to alert the operator if there is any obstacle.
Hi, I am James Longlair and I would like to present about the mechanical system for the semi-automated boat rudder steering system. So this boat engine uses electric brushless DC motor, but for the actuation for it to move or tilt from left to right, it uses electric motor which is servo motor. So this movement converts from the rotary motion to a linear motion, which helps it to move left and right. The next part will be the frame. So for this frame to store the storage system, which is the container, the frame was designed to be a rectangle shape because this will prevent the Nipa shape container from slipping and will oppose any horizontal forces caused by the boat movement. This is good because it provides more robust shape for the boat hull and increase the boat stability in rough condition.
A very good day everyone. Today I am going to present to you about the material selection for every critical parts. For the first material selection is for the shaft. So the material selection for the shaft is AISI 304 stainless steel because it has the highest density and the highest modulus of elasticity. So basically it is more durable. For the next material selection is for storage container. So basically we choose high density polyethylene because it also has a high density which is 970 comparing to polyethylene. Not only that, high density polyethylene also is a commonly used container in the market. We can see that this container is commonly used to store water and then to store fish and so on like that to keep it fresh.
There are 3 candidate materials for the hull as shown in the slide. Out of the 3, fiberglass was the best choice. Fiberglass is corrosion resistant and low density. It is also widely used for many small boats application. Finally, the easy fabrication process means lower labor skills and costs are required. There are 3 candidate materials for the frames as shown in the slide. Aluminium 512 alloy is chosen because it has decent corrosion resistance, higher than mild steel, which is almost similar to the 5052 but more economical, making it the best choice.
For the thermodynamic part, we analyze the heat generated by the component. So basically, there are 2 heat generated from the component, which is the motor and the battery. So the heat generated by the motor is 74.347 and for the battery is 88.049. So basically the total heat generated is 162.396. The reason why we calculate the heat generated by the battery is to know the heat dissipated from the battery. So as we know, in the blue region, the heat range is between 293 Kelvin until 369 Kelvin. And the maximum heat that can be withstood from the HDPE container is 383.15 Kelvin. So from this analysis, we can see that the heat generated by the battery will not affect the HDPE container. Next is the force applied on the propeller. As you can see, for the front view and the back view of the propeller through the simulation, we can see that the force is evenly distributed between these two propellers. So basically, it is suitable that we use stainless steel to make this propeller because the force is evenly distributed, so there are no major deflection which will not affect the performance of the propeller.
Alright, for this modeling and simulation of this frame analysis, we would like to see the behavior of this structure. Okay, as we applied some exert some forces like the thrust force, which moving forward, the drag force, which moving backward, and the weight, which moving downwards. So you can see that there is some structural behavior such as total deformation and equivalent stresses that act on the front and the rear side of this frame, as you can see from the slide.
For the mechatronic part, this is the flowchart for the electronic system of the board. From the input signal received by the board controller, the speed and direction of the board will be controlled. For the speed of the electric outboard motor, it will have a forward or reverse which is controlled by the electronic speed controller. Other than that, during the board is moving, there is ultrasonic sensor to detect the obstacle. The system will send alert signal to the operator. Last, for the direction, the radar system has a left and right option which is controlled by the servo motor. The electric component for this board are 3.7-volt battery, 48-volt lithium battery to power the outboard motor, electronic speed controller (ESC), which is a device to control the speed of electric motor, servo motor for the radar system, remote control, and ultrasonic sensor to detect obstacle near the board.
Assalamualaikum and good day. I'm Muhammad Haziq bin Sudin with metric number 72743. We present on the manufacturing aspect of our boat. So let's start with determining the production quantity and layout of the boat manufacturing. From calculations in tables 1 and 2, it is determined that we can create 96 boats per year and therefore considered a low production quantity. Because of this, our team has decided to implement a fixed position layout in manufacturing the boats. Given is the factory layout of our boat manufacturing. The process starts at fabrication area number 1, where the workers create a boat hull with fiberglass. The mold is transported to fabrication area number 2 for boat frame installation. After that, it is brought to the painting area for painting and finishing the boat. Lastly, the finished product undergoes quality control checking before it is stored on the dry stacks in the boat storage area.
The fluid mechanics involved are fluid statics and dynamics. In fluid statics, the buoyancy of the boat is established as 8,877 and 78 newtons with respect to all its component materials, density, and volume. This indicates a decent loading capacity suited up to 70 kilograms or 686.7 newtons of NIPA having plenty of safety factor balance. The total drag force that follows the buoyancy analysis is 586.88 newtons. The 660.07 newton thrust of the boat is sufficient to overcome this without issue of efficiency. The total cost per unit boat incurred from all the fixed and variable cost is 49,049 ringgits and 83 cents, with the selling price of 58,271 ringgit and 20 cents. The following graph shows the break-even quantity of 124 units and 7,225,626 ringgits and 80 cents. It takes about a year of the project run to start getting profit, which can be set as the safe zone for project improvement with greater profit scaling. Lesser risks are faced with lesser break-even values.
In making sure that our boat manufacturing project is professionally and ethically implemented, our engineers will abide to the codes of ethics set by BEM, such as own up to their responsibility when accidents happen and reject any form of bribery from anyone. Aside from that, the safety of our workers remain our number one priority by adhering to OSHA regulations. Besides that, we will make sure that the operating hours and the conditions of transporting the NIPA set by our boat follows the Sarawak River Ordinance 1993 in terms of navigation and visibility. Last but not least, we apply a risk management strategy which is hierarchy to guarantee that our boat lasts long by creating flexible schedule for transporting the NIPA sap according to the weather and river conditions.
In conclusion, this semi-automated boat is capable to improve the transport system for the Nipasek. It also preserves the environment by utilization of electric motor to reduce greenhouse gas emission, and it has potential for high production if the production rate of Nipasek is increased for the future.